the Arduino's practical session of focal length of a concave mirror. A concave mirror is also known as a converging mirror because it converges the light rays incident on it. In our day-to-day life, these concave mirrors are used by doctors to see relatively large images of teeth, throat, ear, etc. These concave mirrors are also used as reflectors in torchlights and in the headlights of vehicles to focus light on a particular area. Before going to this experiment, let us know the terminology associated with the concave mirror using a ray diagram.
Consider a concave mirror. As you can see, this is the reflecting surface. As you turn around the mirror, you can see the non-reflecting surface. In the side view, to differentiate the reflecting and the non-reflecting surface, we denote the non-reflecting surface with lines drawn on the surface. The curved line M dash, that is the diameter of the circular rim of the mirror, is called the aperture. It is the part of the mirror through which light rays enter. The center of the spherical surface of the mirror is called the pole of the mirror. It is denoted by P. The concave mirror is a part of the spherical shell. The center of the spherical shell is called the center of curvature. It is denoted by C. When you join the center of curvature C and the pole P, the straight line is called the principal axis. If the incident rays on the mirror are parallel to the principal axis, then after reflection, they meet at a point on the principal axis. This point is known as principal focus and it is denoted by capital F. The distance between the pole P and the center of curvature C is called the radius of curvature PC. It is denoted by capital R. The distance between the pole P and the principal focus F is called focal length of the mirror PF. It is denoted by small f.
I hope you understood the terminology associated with the concave mirror. Now, let us go through the aim of the experiment and the apparatus required to perform this experiment.
The aim of this experiment is to find the value of V for different values of U in case of concave mirror, and hence to find the focal length of this concave mirror by plotting graphs between U and V and also between 1 by U and 1 by V. The apparatus required for this experiment are optical bench with 3 uprights, concave mirror, 2 optical needles, knitting needle and a half meter scale.
Before starting this experiment, it is important to understand the typical setup of the optical bench to determine the focal length of a concave mirror. So, let us go through the setup of the optical bench and the procedure to perform this experiment.
Consider a concave mirror and mount it on the optical bench at a convenient position. Now, place an object needle at 1.5 times the rough focal length of a concave mirror. By adjusting the position of the object needle, you will observe an inverted image of the object needle in the mirror. Now, you need to place another needle on the optical bench known as image needle. Now, you need to adjust the position of all the uprights until you find the image of the object needle on top of the image needle and the image of the image needle on top of the object needle. Now, the distance between the object needle and the lens is considered as U. the distance between the image needle and the lens is considered as V.
Now, you are familiar with the setup of the optical bench and the procedure to perform this experiment. Well, let me take you through the step-by-step procedure to perform this experiment. Here, first you have to find the rough focal length of the given concave mirror.
Determining the rough focal length of a concave mirror. Take the concave mirror, for which rough focal length needs to be determined, and place it in the mirror holder. Face the mirror towards the tree and obtain its inverted image on the screen. Once you get the inverted image, move the mirror forward and backward until you get a sharp image. Now, with the help of the scale, measure the distance between the mirror holder and the screen, which is nothing but the rough focal length. Here, it is 15 centimeters.
After finding rough focal length of the concave mirror, we fix the concave mirror on one of the upright and then mount the upright on the optical bench at a convenient position. After that, we fix the object needle on another upright and then mount the upright on the optical bench so that the object needle faces the reflecting surface of the concave mirror. Take proper care that the tip of the object needle and pole of the mirror should lie on the same horizontal line. As the rough focal length of the concave mirror is 15 centimeters, we need to maintain a distance more than 15 centimeters between the mirror and the object needle so that the position of the object needle comes beyond the focus of the concave mirror. After mounting the mirror and the object needle at their respective positions, we move to the right end of the optical bench to observe an inverted image of the object needle looking into the concave mirror. Closing one eye, looking into the concave mirror, adjust the position of the object needle until an inverted image of the object needle is seen clearly. Here you can see the inverted image of the object needle very clearly, but to locate the position of the inverted image of the object needle, we need to place another needle on the optical bench. This is known as the image needle. So, let us place the image needle on the optical bench. Now, I am fixing the image needle in one of the upright and then place the image needle on the optical bench. Now, looking into the concave mirror, we adjust the positions of the object needle and the image needle until an inverted image of the object needle falls over the image needle. While looking into the concave mirror, we adjust the positions of the object needle and the image needle until an inverted image of the object needle falls over the image needle. Here you can see very clearly an inverted image of the object needle is over the image needle. Now, by giving lateral motion to the needles, we bring the inverted image of the object needle and the image needle in the same vertical line. After that, we adjust the heights of the needles until tip of the inverted image of the object needle coincides with the tip of the image needle. Now look for parallax error. If we move our eye to the right and left, there is a relative shift between the inverted image of the object needle and the image needle. So there is a parallax. To remove parallax, we move the uprights back and forth until there is no relative shift between the inverted image of the object needle and the image needle. Here you can see very clearly that there is no relative shift between the inverted image of the object needle and the image needle. Hence, parallax is removed. After removing the parallax error, we note down the positions of concave mirror, object needle and the image needle. Here, the concave mirror is at a position of 80 centimeters, object needle is at a position of 104 centimeters and the image needle is at a position of 129 centimeters. Now we got one set of observations. For more observations, we repeat the same procedure by changing the positions of the uprights. After noting down all the observations, we need to apply the index correction to get the actual measurements. Once the index correction is applied, we get the actual values of u and v. Now we draw u versus v graph and 1 by u versus 1 by v graph to determine the focal length of the concave mirror.
We have found out that rough focal length of the concave mirror used in this experiment is 15 centimeters. Table for values of u, v and 1 by u, 1 by v. Position of concave mirror. When the concave mirror, object needle and the image needle are placed on the optical bench, the inverted image of the object needle without any parallax is observed over the image needle. Then the position of the concave mirror is at 80 centimeters. Object needle is at 104 centimeters. Image needle is at 129 centimeters. Observed distance PO is equal to U is the distance between concave mirror P and the object needle O, that is 104 centimeters minus 80 centimeters, which is 24 centimeters. PI is equal to V is the distance between the concave mirror and the image needle I, that is 129 centimeters minus 80 centimeters, which is 49 centimeters. corrected distance u is equal to observed distance plus index correction. Index correction is equal to plus 0.4 centimeters. Therefore, corrected distance u is equal to 24 plus 0.4 centimeters, which is 24.4 centimeters. Corrected distance v is equal to observed distance v plus index correction v. Therefore, corrected distance v is equal to 49 plus 0.4 centimeters, which is 49.4 centimeters. 1 by u is 0.040. 1 by v is 0.020. F is equal to 16.38 centimeters. Similarly, u and v values for different positions of the object needle O are the mean value of F is equal to 16.435 centimeters. UV graph concave mirror. Using the values of U and V, draw a graph by taking U on the negative x-axis and V on the negative y-axis. We select a suitable scale. On x-axis, 1 centimeter is equal to 10 centimeters. On y-axis, 1 centimeter is equal to 10 centimeters. Now, let us plot the points on the graph. Join all the points. As you can see, the graph comes out to be a rectangular hyperbola. Now, we draw a straight line from the origin, making an angle of 45 degrees with both axes. This line meets the curve at a point A. Two perpendiculars are drawn from A onto x and y axis. The x and y coordinates of A are same. U is equal to 33, V is equal to 33. Therefore, U is equal to V is equal to R, which is the radius of curvature. In case of a concave mirror, the object distance U and the image distance V are same only when the object is placed at the center of curvature. Therefore, F, focal length, is equal to R by 2. Therefore, F is equal to OB by 2, that is equal to 33 by 2, which is 16.5 centimeters. 1 by U, 1 by V, concave mirror. Using the values of 1 by U and 1 by V, we plot a graph by taking 1 by U values on negative x-axis and 1 by V values on negative y-axis. We select a suitable scale. On x-axis, 1 centimeter is equal to 0.010 per centimeter. On y-axis, 1 centimeter is equal to 0.010 per centimeter. Now, let us plot the points on the graph. Join all the points. As you can see, the graph comes out to be a straight line. Now, extend the line to meet the x-axis and y-axis. The line cuts the both axes at an angle 45 degrees, making equal intercepts OA and OB. F, focal length, is equal to 1 by OA is equal to 1 by OB. Here, OA is equal to 0.060 per centimeter. Therefore, F is equal to 1 divided by 0.060, which is 16.6 centimeters. principal axis of the mirror should be horizontal and parallel to the metal rods of the optical bench. The uprights on the optical bench should be vertical and rigid. Tip-to-tip parallax should be removed between image and the object needle. While locating the positions of the image of the object needle, the eye should be at least 30 centimeters away from the needle. Tips of the object and the image needles should lie at the same height as of the pole of the concave mirror. Index correction should be properly determined and must be applied for both U and V.
I hope now you are able to determine the focal length of any given concave mirror on your own without any doubt or hesitation. Thanks for watching.